Is there a way?
Do you allow me to share? All right, so today I was thinking we'd build or draw up a schematic for a two-stage amplifier and then design a PCB for it. So it's just based on two discrete transistors, and we'll take a look at the schematic. You don't really have to understand it. I mean, the goal of this is to look more at PCB design, but I just thought this would be a neat thing to look at. I know most of what we'll be doing later on is, in fact, digital stuff. So all of the boards you guys will be designing will be primarily digital. However, I think this is just a good skill because there's a lot of sort of complexities with the schematic in this design, and then also just some considerations you'll want to make for layout when you're actually doing your PCB. So I'm going to start sharing my screen. Hopefully all of you have downloaded and installed Autodesk Eagle. If you don't have it, you can probably get that started right now and have it ready in a couple minutes. You just need the free version, so you can just Google Autodesk Eagle free version if you don't have it. Otherwise, you can pull that up. I'll do the same. Hopefully everyone can see my Eagle screen here.
Yep, we can see the control panel.
All right, great. So once you have the Eagle control panel up, just let me know. I guess you can raise your hand in Zoom. I think it's a thing. I don't know how many people are here. 7. You can just tell me there's not that many of us. I'm just going to continue on, and I'll pause a little bit here and there. Just let me know if you have any trouble getting Eagle set up and open. So what I've got here is the Eagle control panel. This is where you access all your files and libraries and everything else. Your libraries contain the parts. So you have to, if you don't already have the parts installed in their parent libraries, you have to do that. But we won't go over that right now. We'll just sort of go into the basics again. So I'm just going to create a new project under one of my project folders here. Feel free to make as many folders as you want. I'm going to click New Project. I'm going to save. Not going to save that actually. I'm going to call this two-stage amplifier. All right. Now, I can right-click again on that project and click New Schematic. And I'm going to have to stop sharing here for a second. Share again. Schematic. Share. All right. So here you have it, just the schematic window. I like to turn on the grid. It's easier to tell like sort of a scale here. So I just press the grid button. Leave it on the default, especially with schematics. Maybe I didn't actually turn it on. At display on, and I like lines. So there we go, now we have a grid. If you're not up to this point, just let me know. I'll give you a little bit longer. Suppose while we're waiting, I'll just go over some of the basic controls here. So up here's your toolbar. The only real commands that I can think of right now that you'll need, of course, are save, and then this generate/switch to board. When we do generate our PCB, we'll just click that button. It'll automatically create a board for us. But we're going to start with a schematic. Here you can also see the sheets. So if you have multiple schematic pages, you can connect to all of those at once. Then we have the inspector, which basically if you click on something in your schematic, it's going to give you details on it. Selection filter helps you find certain things if your schematic's really large. And then design manager is sort of just an overview of all of the parts and items and sheets in your design. So very helpful when things start getting large. But we're just working with one sheet today, so that's all we'll need to do. So the controls are evading me. I don't really remember. Anyways, so once you're here, we're going to want to start by adding a part. So we'll go and click this add part button. All right. And inside the add part window is your all of your libraries. So all of your libraries are listed here. So you probably have less than I do. I've accumulated a bunch of them over time, but you should see sort of basic ones. Particularly, we want transistor NPN. Once you find that transistor NPN, then we're looking for 2N3904, which is just a run-of-the-mill NPN bipolar junction transistor. So was everyone able to find the 2N3904? You can also search for it, I think. See if I can search for something else. Yeah, there we go. So if I search for something else, it's going to show up. So I'm looking under transistor NPN, and I want the 2N3904, and I'm going to click on that, hit OK. And then I'm going to get my symbol. So I'm going to start. I'm going to place one of these. All right. Now, if you hit escape, it's just going to open up this window. You can find another part. We're actually going to do that. So you want to open up the add part window again. And this time we are looking for a resistor. This is a little more annoying to find. We want to use this RCL. And under RCL, let's see, those are surface mounts. We want through hole. All right, so you're looking for the RCL library, which is resistors, capacitors, inductors. It's the default Eagle library. And then we're looking under RUS. The reason why REU is going to give you the same thing. However, the symbol is not something that I'm used to, or probably something you're not used to either. So we're going to use the US symbol for the resistor. And we're going to go with the 0204. It's the most popular through-hole resistor in the selection menu here. So all we need to do there is click on it again, hit OK, and we've got our resistor. Now, you're going to want to rotate this part because we're building, we're trying to connect this to the transistor, the top of the transistor, which I believe you just press spacebar. Oh, no, nope. Oh my goodness, I'm too often. Let's see.
Right click worked for me.
Ah, yes, that's right. I'll just hit OK. Right click. Yep, there we go. All right. So we'll place a resistor here. We'll likewise place a resistor here. We'll place a resistor here. And we'll place one more down here. So these are our 4 resistors. And those are going to set the bias point of our transistor. So these two set the bias point, and then these two set the gain. We won't go into too many details on that. I can send you more information about this circuit later on. Again, this is mostly about PCB and schematics. So once you've placed your items, you can connect them or you can number them. I'm just going to connect them first because I found the easiest. Makes most sense to me. So again, if you want to make a node, you have to click every time you cross the line there. So if I were to just go, if I were to click on this wire, so it's net, the green line, and this one I'm gonna make a connection with. So if I just drew straight and I went like this, these wouldn't connect here. You have to create a node. So to do that, or a junction as Eagle calls it, to do that, you actually have to click on the line and then click again. All right, and then connect this resistor to the transistor and this one as well. And then we'll connect these ones to the bottom like this. All right. So now we're going to build out some more of the circuit. So let me just check my schematic. Any questions to this point? All right. So next we want to give our, we'll actually do the values last. So we'll build a whole circuit and then we'll do the values last. So we're gonna now need a capacitor. So if we go to add part and you search capacitor, and we take a look at CEU, again, I'm gonna use the EU symbol because the US symbol looks a little too much like a polarized capacitor. It can get confusing sometimes. So I use the CEU symbol, and I'm going to use, oh, where is it? I believe this is what we want. All right, yeah. So in CEU, I'm searching for the 24X044. And this is just a small through hole capacitor. So C-EU 050-024 X044. All right. So once I've got that, I'm going to place that here, rotate it once, and connect it up to the base of the transistor. All right. And now we can go ahead and add some, we'll start with this first stage. So we'll add the connector for the front, and then we'll add the output for the first stage of the amplifier. So we're looking for a connector. Let's see if Eagle has the audio one that I was looking at earlier. Oh, when I share my screen, does it not show the Eagle part finder?
No, you're good.
It shows it?
Yeah.
Okay. Show the schematic to pull up.
No, it does not.
Okay, that's fine. All right, we're looking for this connector. Oh, there we go. RC is a little big. Let's go to this. Actually, you guys don't have that library, do you? There. Let's see what we can find here. So occasionally, what I'll do, if I don't know what part I want, I'll go through and see what Eagle has in the libraries already. And I'll just scroll through all of them and see if anything has what I need. So in this case, I will accept any 2-pin connector, except these ones. Coax, coax, coax. Let's see. Six JST. Molex. This is what I want. Yes. Okay. This is what we want. So if you search, I think con Molex, if that doesn't help. If you search Molex, so Molex is the name of a brand that makes connectors. In this case, we just want a 2-pin connector from them. So of course it evades me now. Let's see if we can find it. So everyone able to find the Molex library?
Yeah.
Okay, good. So any one of these 2-pin connectors, I'm going to use this one, KK-156-2.
When you get to Molex, what sub-library do you have to open to get there?
So I see we're in con Molex, and then I'm scrolling down to this one. So the name of the library is con-Molex.
You can also search for KK-156-2 and it pops up right there.
Yeah, I can actually just copy.
Yeah.
All right. Is everyone able to find this? Anyone stuck on something? All right, so we'll just insert this part and I'll rotate it so it looks nice. And we'll draw that. So, oops. And I want to connect this to my capacitor. I want to connect this side to the bottom of that resistor. All right. Let's check. All right. So we can move on to the next stage of the amplifier. So the nice thing about Eagle is that you can just click on a part you want to duplicate. And either go right click, and I believe there's just a duplicate button. You can also pattern if you want to do things geometrically. In this case, the fastest way I found is just Control C, Control V, or if you're on an Apple computer, Command C, Command V, I think. And you're going to want get another transistor here. So what we're building here is the first stage of the amplifier. This is a common emitter amplifier. And a common emitter amplifier has a pretty high, we'll call it output resistance, which means if you want to drive something like a speaker, you're going to have trouble because you're not going to be able to provide enough current to the speaker. So what we need to do is take the signal that we amplify with this common emitter amplifier and basically with another amplifier with a gain of 1, we will be able to provide more current to the say speaker that we're trying to drive. So just check this here. All right. So we will go ahead and connect the collector of our first transistor to the base of our second transistor. All right. And then we will connect the collector of our second transistor to the top of R1 here. And then we will take one of our resistors, we'll copy this, we'll place it below our second transistor, and we will wire that from the emitter to the bottom of that resistor. And now, when I've connected two nets that have different names, so a wire in your schematic is called a net. When you connect them that have different names, you need to essentially assign one name to them. So this is helpful because if you connect two nets that weren't supposed to be connected, so you accidentally connect ground and power, you can't do it by accident, it'll tell you. So I'm just going to click OK, because I don't care what the name of that net is. And we will get those connections made there. All right. So, is everyone up to this point? Seems like everyone's good. Continue. All right, so next thing we need to do is see, AC couple the output. So the output of this common emitter amplifier comes off the collector of the transistor. The output of this amplifier comes off the emitter. So we will take the we'll take another capacitor again. We actually won't be able to use this one, so we're going to have to get a different capacitor. So we'll go ahead and click Add Part. And this time we actually are looking for a polarized capacitor. So I believe C pole. Nope. Sitor. Yes. Well, of course, the Eagle search tool is not my friend. So I like the US symbol for polarized capacitors. So again, I'm looking for popular ones because that is what you will be able to get cheaply and easily. So we're looking for this C pole-use 2.5-6. See if I can copy the name. So it's a 6 millimeter diameter through-hole capacitor. So I will place that one. Now, with parts that are polarized, you have to pay attention to which way the plus is facing. So I think I know which way it faces. Let me just check. Yeah. So, oh, it disappeared. Let me grab it back. Okay. So it's going to face the left. So the plus is going to face the left. We're going to connect this to our transistor here. And we'll just click on the emitter and connect it to the positive side of our polarized capacitor. All right. So at this point, we can add the rest of our components. So we're going to grab our connector. We're going to need two more connectors, actually, one for power and one for output. So let's see if I can actually click on this. I don't think it'll let me. I guess we're going back for that. Rolex. again is this KK-156-2. If you're able to copy and paste it, let me know. I wasn't able to. So again, I'm just gonna insert that
I
again.
just used the select tool and dragged both of them in the box, and then I was able to copy and paste.
Okay, perfect. Let's try that. We're gonna do another one. There we go. Yeah, that works. You just have to select both terminals of the connector. So I've placed another connector up here. And then we can connect one side of this connector to capacitor, and then one side to this line on the bottom. All right. Now we need something to power our amplifier, because of course an amplifier is an active circuit. You have to provide power for it to work correctly. Of course, because the output power is greater than the input power of a signal. So what we'll do is use something very useful in all CAD software. That's defining a ground. So ground is just sort of a global reference for your circuit. You might think of it as 0 volts, or like the large prong that goes into the wall. Again, for now, we can just think of it as 0 volts, but when it comes to PCB design, it generally means anything but 0 volts. So in this case, it's not something we have to worry about much. So I will just go into the add part and search GND. This gives me a couple options here. I'm going to use the one that shows me the value of the net. So this is going to be under supply 1 and then ground. So if I click there, click OK, I get this symbol here. I'm going to put this next to the bottom terminal of my third connector. And I'll wire that up. And then the other nice thing that Eagle gives you, potentially, give you this. Ah, it does. Nice. All right. So if you search supply, then go under supply 1, we're looking for any one of these supplies. These different symbols are helpful in differentiating different power rails that you may have on one board. So in this case, it's easy for us. We need 15 volts. So we are going to take the 15 volt rail. Let me just make sure that's right. I might be 12. Nope, it's 15. All right, so we'll take the 15 volt supply 1 volt, hit OK. We'll put it up here by the other half of our connector. And we will connect another wire. So just a quick note about supply symbols and schematics. So a supply symbol includes, power, and then also ground symbols can sometimes be considered supply symbols. It's important how you orient supply symbols. If you notice, the negative voltage rails here are pointed downwards. Now, this is helpful for someone looking at a schematic because they can look right at those symbols and know exactly what kind of voltage rail it is. In this case, it's really best when placing ground symbols to point them downwards. I place them sideways sometimes. It's when schematics get really crowded, it's hard not to. Same with voltage symbols. Again, if you're going to place those, keep them upwards, and if not, sideways. So sideways is okay. It's still understandable. The voltage symbol, or the value is still there. But again, try to keep them upright for voltage symbols and facing down for ground symbols. Don't do them reverse. So don't put ground symbols like this. It gets confusing when you have lots of them, and in cases where your ground symbols aren't labeled with ground, it's even more confusing. So in this case, we'll just point our ground symbol down, and we'll take another ground symbol and we'll connect it to this bottom line on our circuit. And it's going to ask me if I want to rename the net ground. And yes, I do, because I want it to connect to that connector we just made before. So I'll click yes. All right. And then I also want a supply rail up here. So I'll copy that 15-volt symbol and I'll put it on the top there, and I'll allow it to rename the net there as well. All right. So now that we've done that, we have our power and we have our ground. Are there any questions up to that point? All right, fair enough. I'll keep going. So with power rails, they're never perfectly 15 volts. There's always some fluctuation, whether that be from the power supply or some circuit element within your design. So on most designs, you'll see that your circuit has been, hold on one second. All right, so again, yeah, power supplies aren't always perfect voltages. So essentially what we need to do is supply some sort of buffer for the power supply so it can fluctuate a little bit, and we need to compensate for that. So we'll use another polarized capacitor. So in this case, we can just take this guy here, copy it, and bring it over to our supply. And feel free to do this how you like. Put it between any power and ground. So I'm just gonna move this one over here to make it look nice. Likewise, I'm gonna do this over here, make it look nice. All right. So now I have my 15-volt power rail, what we call decoupled with a capacitor. So equal can be frustrating sometimes. All right, there we go. That's good. All right. So now that we've done that, we can go ahead and apply values to all of our components. So resistors, they have a value of resistance in ohms. Capacitors have a value of capacitance in farads. So in order to give all your components values, you have to go over here and click the value button. So once you've got the value button, you can simply click on the component you want to revalue. And you should get that window right there. I'm just gonna make sure I put the right numbers here. And so this resistor that's gonna set our bias point is a 47 kilo ohm resistor. Now, when you're drawing schematics, you don't have to include the unit. So I don't have to include ohms. I could write 47,000, and that would mean the same as 47K, because K is, of course, 10 to the third, it's kilo. There's also milli, mega. That's about it for resistors. You'll see milli, ohms, see ohms, you'll see kilo ohms, and you'll see mega ohms. But we're sticking with kilo ohms, so 47,000 ohms. And then this one is a 10K or 10 kilo ohm resistor. So I'll just type 10K. All right. Everyone get that? All right. Works for me. All right. So up here, this resistor is a 2.74 kilo ohm resistor. This one is a 1 kilo ohm resistor. I believe that one is, yep, 820 ohms. So this one's just 820. And so I don't have to include any sort of K or anything there. All right, and that covers all of our resistors. Now for our capacitors, we're working in farads. Again, we don't need to include the farad part of the unit. So we'll just include the value. So for this big decoupling capacitor here, it's 47 microfarads. Now micro is normally given by a mu, the Greek letter mu, if you were to write it on paper. U looks pretty darn close to that. So in electronics, we use the lowercase letter u to say micro. So 47U means 47 microfarads, or 47 millionths of a farad. A 1 farad capacitor is enormous. We're working in very small capacitances here. So we'll hit 47U. This one over here is going to be the same thing. It's 47U. All right. And then this one here is way smaller. This one is 0.22U, or the other way you can write this is 220N. So 0.22U is 0.22 millionths of a farad, or 220N is 220 billionths of a farad. So N is times 10 to the minus 9. We're working with nanofarads here, so we'll go 220 nanofarads. It means nano. Hit OK. All right, and that gives us all of our resistor values, all of our capacitor values. And now there's certainly some modifications you can make to this circuit. I'm sure many of you have heard of potentiometers. You can use a potentiometer in place of this 1K resistor and with some series capacitance, and make a basically a volume knob, so you can adjust the gain of the amplifier. And you can also include like proper audio connectors if you wanted to connect this to an actual like headphone system or speaker system. This can actually probably drive a pretty big speaker. Nothing enormous, of course, these are small transistors, but certainly would be possible. So the other thing before we move on to throwing this on a board is just to look at our component names. So right next to the value command is the name command. So let's say I want to rename my components so they're a bit more orderly. So I'll just click on the part. I can rename this one R1. Oh, doesn't let me do that. So I guess I have to start over here. That kind of stinks. So I'll just name these random things. All right, so this is R5. I'll make this one R4. Make this one R3. Make this one R2. Make this one R1. Hit OK. Now, Eagle can also do this automatically. I think it's a script or ELP. I can't remember. Oh, yeah. So these ULP commands, they're basically little scripts that can run and do automate things for you. So if I open that command, I can auto renumber my sheet. Of course, that. Oh, goodness. Does some weird stuff, but it eventually fixes it. Just numbered it slightly differently than I would have, but that's okay. I just wanted to demonstrate a point there. But that's it for a schematic. Are there any questions here before we move on? All right, so once you finish your schematic, I want to check it a few times. In this case, it should be fine. We will go to our board, so I can just click this generate/switch to board. I'm going to click, it's going to ask me create from schematic, and I'll click yes. And do you see the board view on my screen? Or is it still showing the schematic?
Nope, we don't see the board view right now.
Let me stop sharing. Share. All right, now you should see it, I think. All right, so you can see all the components I've added. They're nicely labeled, actually. So what we'll want to start with first is resizing our board. So generally, when you're designing a PCB, you work from, if you're like a career PCB designer, you'll get electrical schematic from an electrical engineer. You'll get a mechanical drawing for the PCB from your mechanical engineer. And as a PCB layout engineer, your job will be to basically take into account the schematic drawing and the mechanical drawing and build it into a PCB. In this case, we're doing all of the steps ourselves. So generally, we'll set the board size first and try to work our circuit into that size. You can, of course, make things bigger or smaller as you need, but if you have some sort of mechanical constraint like an enclosure or something like that, you have to make that consideration. So we will just go and size our board down a little bit. Again, the PCB viewer works in grids. So I'm going to just turn my grid display on, and I'm going to use a 50 mil grid size. All right.
Sorry, how do you open board view again?
Yeah, so if you're in your schematic, you click this button, it's going to say green, it's going to be green with a board.
Got it, thanks.
Yeah, perfect. All right, yeah, so when you're in the board view and you want to resize your board, you just go to layer 20, which is dimension. So just like Photoshop or something like that, you have different layers, except layers on a PCB mean layers, physical layers in the actual manufacturing process. So top and bottom are layers of copper on the top and bottom of the board respectively. And then you have your pads and vias, which just designate areas of your board that are to be made connections to components. It's unrouted thing, basically just showing you these yellow lines where things are not connected. That's not a physical constraint on your board. Dimension is, of course, the size of the board. T place and B place are these silkscreen layers on the top and bottom layers of the circuit respectively. So all of this here is T place. B place is on the bottom. These layers aren't important. Names, of course, names. So R5 is on the T names layer. And then T values, I believe 820 would be in the values layer. Yep. All right, so if I want to change my board size, I'll go into the dimensions layer. And I will just drag one edge over. And I'll make it, let's go 2 inches by 1.5 inches. So there's 2 ways you can do this. You can either type in the values here. So these are weird. So I'm just going to click on the lines I want to edit and change those values. You can also drag, I'm watching up here when I drag the lines around because that shows me the coordinate of my cursor. And if you have your grid on, the lines should sort of snap into place. All right, once you've done that, you can start placing your components. So I'm going to start with my,
I'm sorry, what did you want the dimension be?
you can make it whatever you want. I made it 1.5 inches by 2 inches. So
Okay.
Eagle works in mil. By default, mil is one mil is 1/1000th of an inch. So 1,000 here is equal to an inch. If that makes sense. So I'm just going to go back to my schematic quickly and take a look at which connector number is my input. It looks like X2 is my input. So I'm going to take X2, I'm going to spin it around, I'm going to place it sort of in the middle of my board. All right, then my output connector is X3, so I'm going to take that, again, place it on the other side of the board in the middle. And then X1 is my power, so I'm going to place that in the middle but at the top. Again, there's no real reason to why I'm placing these here. It's sort of just like visually, this is how the board functions, left to right, input to output. Power is at the top. It's kind of like our schematic. And more complex boards, this will almost certainly never be the case. But in things like this, where you can make it look exactly how you want and it makes logical sense looking at the PC board, then it's quite nice. So, all right, so taking our input, or actually our, looks like this one is, yeah, this one's our decoupling capacitor. So I'm going to place that up by my power input here. Then you can also, when you're dragging things around, you can sort of just follow these yellow lines to where it's taking you. Just going to keep doing that and sort of just keep placing things to wherever they look nice. Again, this one should go here. So that's our input AC coupling capacitor, and then this is our output. So again, I'm just going to right click to rotate things into place. And you'll see as you drag things around, all of these yellow wires will start crossing more and more, and it'll be hard to tell what's going on. So what you'll do is come over here and click this rat's nest button. It looks like an X with 5 dots in it. So if you just click that, Eagle will reorganize all of the air wires, the yellow lines, to the closest pins. So you can see that this is now connected here. So it reorganized them to the closest pins nearby. All right, so to make this look nice, I'm just going to rotate this around. I'm going to move this up here. I'm going to rotate that transistor. All right. I've got those. I can start placing my resistors. So again, this is our gain setting resistor, along with this one. Just going to set the bias point. And generally, I try to place things to keep the paths as short as possible. And I'll place them sort of in a logical way, so I don't have to route them. I don't have to route things in weird ways. You can also try and place components so that they're sort of even and symmetrical. That always looks nice. In this case, you can see how I've laid things out here. So I would just sort of place it however you see fit. Try to make the air wires as short as possible, but give sort of a reasonable amount of space between all of the components. If they're too close, not only will it'll actually tell you something's wrong later, but it'll make it harder to assemble, even if it passes some sort of a rule check. All right. So I'll give you guys a few minutes to do this. Let me know if you have any questions. You guys able to fit everything on the board? Nice. Just let me know when you're ready, and I'll get started again. I don't think there's any huge rush. This is, in many ways, barely scratching the surface of a PCB design. But I think it's interesting. I've made a simulation of the circuit, so although we won't be able to build it, actually I can bring the stuff to build it if we're in the lab tomorrow.
We're not going to be in the lab tomorrow, but yeah.
Well, next time we're in the lab, I can bring the stuff to build it, and we can see if we can use our iPhone to play a speaker.
That would be pretty cool.
Yeah. All right. So I'm just gonna keep moving here. Stop me if you have any questions or you want me to wait or something. 1 second. I will. All right. So once you've drawn the board and got your components on the board, you can begin connecting all of your traces. So in order to do that, you click this root air wire button. And what this will do will allow you to click on any pin, and then it will highlight the other pin, and then from there you can just go ahead and click. In this case, I'm going to undo that trace because it's really, really thin. So right now the width of the trace is 6 mil. The 6 mil is pretty standard for like small circuits, but in this case, since it's analog and since it's not super, we're not space constrained, we should basically use not the biggest trace we can fit, but something that looks more reasonable towards the pin size. So I'm going to go with 20 mil. I think that's pretty good. So to change the width, you just go up here to this drop-down menu and select your width. You can also type them down here if you need to do like a weird width, like 21 or something like that. But I'm just going to stick to 20. So I'm going to click on the pin I want to connect. The next one should highlight, and I just click there. And then I basically just continue. And I'll do that for every net except for ground. So wherever you see ground, don't connect those yet. We'll do those at the end. So I'm just going to keep on doing this. So I'll just do a quick sort of preliminary routing here. And then from there, oops, this might be a problem. I'm going to reorient this. And it should be possible to get all of your traces on only the top layer. Now, we can put vias, and vias are essentially through holes to pass signals from one side of the board to the other. However, I'm going to try to avoid them for at least this part of the layout. We'll discuss them shortly, though. So again, I'm just going to continue connecting all of my traces. I'm just reorganizing some of my components because it would have made it impossible to route only on the top layer. Please stop me if that was confusing or something. All right, so I'm just going to keep routing signals. Until all that's left is ground and 15 volts. So for 15 volts, I'm going to route an even thicker trace. I'm going to go 40 mil. And I'm just going to try and make it look nice. And I think that covers all of the 15 volts. So now everything that's left says ground on it. And all of my signals are in red, meaning they're on the top layer. All right. So the way I'm going to do the ground is called a polygon pour. Now, using polygon pours to make your grounds tends to improve the signal integrity on your board. So if you have really high frequency signals, or you're drawing lots of power, things like that, it's generally good to keep your ground planes completely solid. So to do that, I'm going to switch to the bottom layer. So I'll just go up to the layer here and select 16 bottom. And then I'm going to go and find the polygon button. It looks like a pentagon. And then the polygon tool pops up. So all I need to do there is just draw a rectangle around my board. And then once I close the rectangle, I'll see that I can name the signal of the polygon. So in this case, I'm going to type GND in all capitals. I'm going to hit OK. All right, now I've got this dotted blue line around my circuit board. And to actually fill the board in with copper, all I have to do is click the rat's nest button again. All right, and then that fills all of the board in with copper and connects all of the ground connections here. You can see those are connected with thermal reliefs. So these thermal reliefs are just thin pieces of copper that make it easier to solder your components onto the board. So just going to switch back to my top layer and take a look at the full stack up here. So you can see all of my signals are routed on the top layer, and my ground plane fills the entire bottom of the circuit board. All right. Now, let's say that I was having real trouble routing a certain signal on the top layer. Like I couldn't go around something, or it would have just been I would have had to go like a whole loop around the entire board. In that case, I can switch to the bottom layer. So I will use, let's use net 2 as an example. So I'm just going to rip that one up. All right, and then I'll go to root airwire and switch this back to 20 mil. All right, and then, I forget the command to switch layers.
Spacebar will place it via.
Spacebar doesn't? All right.
Spacebar does it, yeah.
Yeah, Altium is Control-Shift-Scroll.
Whack.
So spacebar places a via, and a via is essentially just a really small hole from one side of the board to the other. And this is going to basically connect the top trace to the bottom layer, and you can start routing on the bottom layer. Now, say I had to go under something, then all I have to do is route my trace on the bottom layer, press the space bar again, and that's going to bring my signal back to the top layer. And then I can finish connecting it, and there I go. I have a signal routed on the top layer. And if I needed to, I could in fact route something over that. And in order for those changes to properly take effect, you have to click rat's nest again, and it will clear the polygon around the trace. All right, any questions there? I think I went kind of quickly, but I'll got that. It's good. All right. So that is basically it for layout. So once you've connected all of the signals and you see no more of those yellow lines, it means you've connected everything. And to confirm that, what you can do is go here and click the DRC button. DRC stands for Design Rule Check. And under the DRC, you can configure all of the controls, or basically all of the rules for your PCB. And these rules are generally defined by the company who's going to manufacture your PCB. Unfortunately, those rules are things that we can't set. Some of them are nearly impossible to manufacture. For example, if I change the minimum width of my traces to 1 mil. Oh, that's not width, that's clearance. Sizes. So if I change the minimum width to 1 mil, that would mean I have a trace of copper that's 1/1000th of an inch wide. And that's really, really hard to make. So that would cost a ton of money. In this case, 6 mil is the minimum. That's pretty much the industry standard for the smallest size you're going to get on a cheap PCB. If you have to go any smaller than that, you're going to start paying lots of money. All of these other things are things you can find on your manufacturer's website. So in this case, all of this is pretty much exactly the same as the cheapest PCB manufacturer that exists, their JLC PCB. If you want to know more details about what their design rules are, you can find their capabilities. So if you Google JLC PCB capabilities, it will show you what their basically minimum sizes are. And then you can go in here and go tab by tab and reference their table and then fill in all the information in the table in Eagle. The other way you can do it is I think JLC PCB and other PCB manufacturers actually allow you to download a file. So you can go in the first tab of the DRC and click load. And you click load, you download the file from JLC PCB, you load in the file, and it automatically fills in all of the rules. So once you've established all of your rules, we can go ahead and click check. And what check is going to do is tell us if there are any errors. In this case, it says DRC no errors. So if there are no errors, it'll just say no errors. There's no pop-up, there's nothing. If there are errors, they'll pop up in a window and it will list each one of them. And then you can go down the list, it will highlight an error and you can see them. So I'll just make one for an example. So if I went like, it's not even gonna let me make an error. Ah, there we go. Oh, no. Can it let me make an error? I have to turn this off. Nope. Ignore. There we go. So I can make an error. And it'll actually tell you before you even run a design rule check that there's an error there. If I run DRC again and click check, it'll say not only that there's an overlap, there's two in fact, that there's a wire stub. So in this case, all I have to do are go in and delete the problem traces. And DRC again, and there are no errors. That's great. So theoretically, I could send this out to a manufacturer and all of the connections would be good. So the last thing is generally on a PCB, you don't have to include the values. Even if you're assembling the parts by hand. Because when you assemble the board by hand, you'll print out a schematic as well. And you guys already did this. You saw the schematics for the Arduinos. So you print out a schematic and follow that to assemble the boards. So in this case, all of the values, I can actually go ahead, click and delete them. So Eagle makes this a pain. Just click the group icon, click on the values. I can go around and delete those. I'll keep them for the resistors because they've actually placed them nicely. They're kind of convenient for resistors, especially when they're like inside the symbol, because then they'll be hidden when they're done. I'll also delete the transistor values. All right. And then the names, I'm going to want to move around so they are where I want them. So they're visible, they're not overlapping stuff. And they make sense in terms of their placement. So something with when you're designing PCBs is that when you place these names, if you don't place them well, especially on very, very compact boards, what will happen is that it becomes confusing, like extremely confusing as to the orientation of a component. So for example, if I were to rotate this name and put it here, if I had another resistor that was, for example, like if this resistor was also, there's another resistor over here, right? And I had two of them, it would be confusing. Is R1 this resistor or is R1 this resistor? So it's just important that you sort of orient the text in the same direction as the component. So in this case, I've done that for all of them here. You want to make sure there's no overlap of silkscreen, otherwise you won't be able to read it. Otherwise, that looks good. All right, and so I can go and if I want to put my name on the board or something like that, I just click the text button. I'll bring up this little prompt, so I can say two-stage amplifier and I will want to change the layer to T names works, and I want the font to be vector, and I want the size to be 50, for example. So I can put that there or here or something, and then I can go and put my initials or something, or the date or whatever you want. Like that. Same thing. And there you go. All right, so that mostly concludes the PCB design. I think we'll get into more advanced stuff later on. Was for what we covered, that was fairly short, I think. Computer's about to die. Plug this in. Are there any questions about any part of this before I show you guys the simulation? All right, fair enough. Let me stop the share here. I'll pull up the simulation. Where are we going? Zoom, share screen. So Firefox, share. All right, so I think you guys can see the screen now. Is that correct? Does everyone see this?
Yeah, you're good.
Yeah.
All right, so the yellow, or the red, sorry, the red is our input signal. So on the left side of the circuit, we have a 1.5 kilohertz sine wave. So that would be like a, I don't know, you can just Google a tone generator and have it make a 1.5 kilohertz sine wave. So it's just like a pure tone. It's an audible tone. You can hear it. Then we have our circuit here with something. Did I miss something? Uh-oh, I might have missed something. No, I didn't. Oh, yeah. No, we placed that. The simulator doesn't like loops with capacitors and no series resistance. So I just why that this is here. So this should be in our thing. It's 47 micro, and it has a series resistance, but this ideal component doesn't. So anyways, so you can see that our output signal is significantly greater in amplitude. I think it's like a gain of 3, and you can do the math to find the gain. I'll send you guys the paper where this whole circuit came from. And you go through, you can do the math, you can read all about the circuit and how it works and its applications and its limitations. But you can also see that our output wave, the green one, is inverted. So that's a consequence of a number of the components in the circuit. We can actually find out which one. So if I draw inputs and sources, and I went outputs and labels, voltage meter, scope probe, and put one there, and view in new scope. Scopes. Combine all. I forget which one it is. I think it's probably the that input capacitor or the input first stage of the amplifier. Anyways, you can find out the details in the paper. I'll send it over in the Discord, I think. Hopefully we can build this and try it out once we get into the lab. But and if you have any questions in the meantime, just shoot a message in the DPF or the intro Avionics channel. or send me a message on Discord. I'd be happy to answer any questions. If you have any projects that you want to work on, happy to help out with those. Just let me know. So I think that's all.